All right, we're going to look at some piecewise limit problems. This example, find the values of a so that this is continuous at -1. We can see this piecewise function is changing here at -1, so that's where we would want to check to make sure that it is continuous. These two functions on their own are definitely continuous. They're not rational functions or polynomials. So what we want to do is see, does that limit exist there as we approach -1 from both sides? So let's check our limits and see what we should get. So first one, what if we did limit as x approaches -1 from the left? Well, then we would be choosing this top function here of 3ax plus 7. Substituting in -1, we could see what this will end up equaling then. So it'll be 3a times -1 plus 7, which would be -3a plus 7. We don't have a way of solving that for a, but let's continue on here. Now let's look at what's the limit as we approach -1 from the positive side. Well, now that's going to be this bottom function because that's when it's to the right of -1. So we would want to use x squared plus a, substituting in -1. This is going to end up being 1 plus a. Well, again, we can't solve that for a either, but we know if this is continuous, the limit needs to exist, meaning the left and right sides need to equal each other. So what we want to do now is set these equal to each other, because again, we want limit as x approaches -1 from the left to equal limit as x approaches -1 from the right. So setting these two equal to each other and solving, we should be able to get a solution. I'm going to subtract 1 here and add 3a over. And so it looks like a needs to equal 6/4 or 3/2 or 1.5. So when a is 3/2 or 1.5, then this limit exists. It would also have that same function value there because that's where it would be equal to -1, and so all our continuous things are completed. All right, let's take a look at another one. Define the value of g at -2 so that g will be continuous at that value. Well, if we try plugging just -2 in here, I think we're going to run into a problem because this would be 4 plus -4, which equals 0, and we can't have division by 0. And so our function is not defined at -2, but that's what they want us to do. They want us to figure out what should that be so it's continuous. Well, the other thing we know is that the function value needs to equal what this limit is. So let's see what is the limit here of this function as we approach -2. In order to do that, think back to some of the previous videos we looked at. How can we solve this even though we can't plug that in? Well, it looks like there is some factoring here we can do. So let's factor both the top and bottom here, x minus 5 and x plus 2. The top factors 2. On bottom we can factor out an x plus 2. Those would cancel. Now we can plug in -2 because we don't have that problem anymore. And it looks like we get -7 over -2 or 7/2. So if x equals 7/2 or 3.5, then this would be continuous. So in order for this one to be continuous, we'd want g at -2 to equal 7/2. All right, another piecewise one here. Use the definition of continuity and limits to determine whether or not k is continuous at 2. Well, we know from right here that k at 2 equals 5. So it has a value of it has a function value at 2, so that was part of our definition of continuity. But now we also have to test the limits. This limit needs to exist. So what I want you to do, like we did on a previous one, is pause and see if you can find both the limit as x approaches 2 from the left, and also see if you can figure out what's the limit as x approaches 2 from the right. Okay, let's see what you did. From the left, we'd want to use the one where x is less than 2, so this would turn into 3x minus 2, which, substituting in, gives us negative 6 minus 2, or negative 8. On this, oh, sorry, not negative 2, positive 2, and so this should be 6 minus 2, 4. On the other one, if it's from the right, now that's that condition, so we'd be using the function x squared, plugging that in. We now get, sorry, 2 squared, or 4. So that tells us that the limit here does in fact exist. The limit as we approach 2 for this function, k of x, not f of x, k of x equals 4. So would this be continuous? So here's where you got to be careful. Just because our limit existed there does not necessarily mean this is continuous. The last part is what we got here, equal to the function value. And as you can see there, those are not the same. And so in this case, this would be discontinuous because k at 2 is not equal to the limit as x approaches 2 for k of x. So one of them we got 4, the other one's 5. Those are not continuous, or those are not the same, so not continuous.